Okay, let's get started. In the last class, we talked about several defensive approaches to defeat stack-based buffer overflow. We talked about direct approaches, which may be very expensive. Then we talked about what was the first one I talked about? We talked about channel stack. We also talked about DEP, right? So today we will talk about the third approach, which is stack cookies or stack Canary. There are many different names for it, but the basic idea is the same. This is also a very intuitive approach. When you look at how it works, you are saying, okay, everyone can come up with an approach like this. So this approach was introduced back in 1998 and was published in Unix Security, which is one of the 4 top security conferences in our domain. Unix is an organization. They have all kinds of system, network security conferences, and the Unix Security is dedicated to all kinds of security problems. So the paper title was Stack Guard, Automatic Adaptive Detection and Prevention of Buffer Overflow Attacks. So the idea of this is very simple. This is a compiler level approach, which means C programmers do not need to change their source code. They do not need to do anything. This is totally transparent to them. This compiler will try to inject or instrument some instructions in the function prologue and epilogue. So we have same compiler-based approach already. The shadow stack approach, which was last class, was also a compiler-based approach. It was also transparent to say programmers, right? We add several instructions at the beginning and ending of function, and that is automatically done by the compiler. So in this stack guard approach or stack cookie stack Canary approach, the compiler will instrument some instructions to put an additional value onto the stack. And that additional value is called Canary. And at the epilogue of the program, the function, there will be instructions to check whether the Canary value has been changed. If it is changed, then you were saying, oh, there has been a buffer overflow there. That's the idea of it. Okay, very simple. So we are going to use the overflow return 4 as the example here. We have already seen this program multiple times. We have a main function called Overflow. Overflow has a buffer, 30 bytes at C code level. Then it calls gets, which is vulnerable, which is dangerous. May give you more bytes than 30 bytes to overwrite the stack, right? So we have 2 versions of this overflow return 4. One is the left-hand side. You have the version we have been hacking for several classes. So this one is not protected with the stack Canary. So we have this call to gets. Before that, we push the address of the buffer onto the stack, which is at EBP -30. So you are already familiar with this. So on the right-hand side, we have the stack Canary protected version. Okay. So to compile this version, you only need to add a flag, a GCC option when you compile this program. So you can see this version is much longer than the previous version. The previous version has maybe 12 instructions, but this version, the same source code may have like 25 or 30 instructions. So what is important here is in those two boxes, okay? So gets is still here. Before gets, the offset of the buffer also changed a little bit, as you can see here. The offset of buffer changed to 34, but this is not, actually, this is directly related to the stack canary. Before that, the distance between the buffer and saved EBP was 38 hex, which was 48 bytes. Now there are 4 more bytes, right? And that 4 more bytes are used for the stack canary. So here we can say that in the first box, we have a move instruction to move some data from GS and the offset of 14 from GS. That's a memory location. GS is a general register. We haven't used this before. We talked a little bit about this in shadow stack, I believe. Yeah. We saw example using GS in shadow stack. Anyway, so this pointer actually GS points to the something a data structure called the thread local buffer. So it's a data structure in every thread. So GS points to that. So from the 14th offset in that memory location, we're moving 4 bytes to the register ECX. Then we move the ECX to EBP minus C. Okay. So which means the EBP minus C, that address, that 4 bytes, is a stack canary. And the canary value we're getting from the thread local storage. After that, we move 0 to ECX, then we call gets. So if the gets override, so from the source code, you don't really see the canary value. Okay, it's a dynamically generated value when you launch this program. It's a random value. But there are some heuristics as well. For example, for most of the systems we are using, even though canary value is 4 bytes, where one of the bytes is 0. Okay. So only 3 bytes are random. Then after we call gets, after balancing the stack, eventually before we return to the main function, in this box, we have some additional instrumentations. Here, we are moving whatever is in EBP minus C to ECX. Then we try to compare whatever is in ECX at the original stack canary location, which is in the thread local buffer. So this is very much similar to the stack, the shadow stack approach, right? We compare the return address, but here we're not comparing return address, we're comparing a random address. So here we're not using a compare instruction, we're using inclusive or instruction, but basically they do the same thing, comparing. So if they are equal, then we keep going. If they are not equal, then we will call the function, which is a library function, underscore, that means the library function, stack check fail load. And this function will print out the string and also kill the program. The string will be something like stack detected. Okay. So if we run this program on our server, overflow for cookie. So this program will take input from std-in. So if we just give a small string here, it will say I pity the fool. But if we give a very long one, we're trying to overflow, right? But if we do this, we will not be able to get a segmentation form. Instead, the program output stack / detected, and the program will be terminated. Okay. And this line is printed by that function stack check fail function. Yeah.
Is the random value cryptographically random or is it just?
Well, from what you saw there in that code, right, has nothing to do with how secure that random number is. So how secure that random number is totally a different problem, right? You can get a random number from the OS. The OS can get a real true random number. Yes, that is a related issue for the. Yeah.
But who is deciding the random?
So in this case, we are running an application here. The application is fetching a random number from the OS or whatever place. But for different OSs, like for example, for embedded systems where there is no OS, then it could be a different story. Actually, we had a paper published last year talking about this issue on embedded systems. Basically, this approach is not working on embedded systems. Question?
No. You were something regarding shadow stack.
Shadow stack? So this one is not using shadow stack. What's your question?
Something you would derive from analogy of the shadow stack.
Yes, so remember in shadow stack, at the end, before you make the return, you also compare the return address with the address on your shadow stack, whether they are the same, right? So it's very similar idea here. Here is you put some value on the stack, okay? If that value is overwritten, it will not be the same as what you had before. So you compare whatever is on your stack to wherever you get the random number.
You are here doing an XOR with the value that is on your shadow stack?
No, this is not shadow stack. This is another place. In this case, this place is called thread local storage, actually, TLS. Okay, yeah. Thread local storage or thread local buffer. So a little bit more on that register, GS, right? So it's a system register. That register has been there for many, many years. Even in very early version of 80 to 86, they have this version of register. They were used for segmentation before, but now we are using page-based virtualization. So those registers, they are not used for segmentation anymore. For example, CF at the beginning used for code segment, SS used for stack segment, ES for data segment, extra segment. Okay, well, originally they were designed for that. So now GS in application, it points to the thread local buffer, thread local storage. So this is the layout of the stack frame when we use stack Canary and without stack Canary. So without Canary, this is what you are familiar with, right? We have the buffer, the distance between buffer to save the EBP, 48 bytes. Then we have saved the EBP, we have return. The EBP register points to save the EBP when you execute this program, this function. So the one with cookie and from the source code, from the assembly code, we saw that buffer is at EBP minus 34. So the buffer is actually from here to here. The distance between buffer to save EBP is 34, which is 52 bytes. Then we also saw that there is a Canary, and Canary was at EBP minus save. So, which means the buffer is actually from here to here. So in this case, the compiler actually gives us 40 bytes of buffer, and the previous version gives us 48 bytes. Okay. There are still 8 bytes between the Canary and save the EBP. No one put anything there. Okay. So that 4 bytes is reserved for the Canary. The 64-bit version of the code is similar. The 64-bit version of without Canary, very short. The buffer is also at RBP minus 30, 48 bytes there. The 64-bit version, it's longer. And in the 64-bit version, the register we're using to retrieve the Canary is different. We are using FS instead of GS. So in 32-bit program, we use GS for thread local storage. For 64-bit, we use FS for local storage. And also the offset is different, in this case, 28. So we retrieve from thread local storage a random number. So your question was, who placed the random number there, right? That's a totally different story. Here, we're not talking about that. Yeah. So it could be, say, the libc library was trying to retrieve that in the elite function, everything, and put it here. Then each function, they only need to retrieve from here. We get that value from RAX, we place RAX to RBP minus 8 in this case, okay? So we're not using any buffer between the query and the return address in this case. Then we clear EAX, and at the end, we will compare what we have on the stack and also compare with what we in the thread local storage. Okay. So the overhead of this, you can tell, we have many more instructions. In this case, it's kind of like 9 instructions. Some of them are moving instructions, moving data from memory to compares. And if there are error, well, if there is an error, we do not really need to consider the overhead because we detect the attack. But without the error, that are the overhead. We have so many instructions there. Okay, a little bit about those two registers, GS and FS. So they point to something called the thread local storage, and applications on x86 use those two registers to access the thread local storage, which is a data structure in memory, in the DRAM. And a random query is generated at the program initialization and stored there. So when you store there, it could just be at a C code level, because the C library is also developing C code, right? A little bit of assembly as well. So at a C code level, it's actually just a variable. And that variable is placed at the thread local storage. We can actually use some tools like PalmGDB to get the return address, get the address of that. I think in our server right now, we didn't install PalmGDB. We used to install on another server. So there are several different Canary types or values we can use. The very first one is just a random one. We just generate a random or pseudo-random value and put it there. Or we can use a random inclusive OR Canary. There are also a version just use 0, and there is a version use just the special characters like FF, end of line, those kind of things. But most of what we are saying is still a random value. So this is a figure taken from a paper we published last year. We were analyzing how effective stack query is on embedded systems. So you can see that, I mean, after finishing this class, technically you can do all kinds of research with me, find the problem, we identify the problem, we come up with solutions, and we can publish papers together. So this is not necessarily a very long paper, it's a short paper we published last year. So in this paper, we analyzed how the stack canary was generated and used in microcontroller systems, those low-end IoT systems, and also Linux. So in Linux system, the kernel has its own canary. The kernel also have functions, right? So as long as there are functions, the function can be protected by canary. Then the kernel has its own canary. And each application, when they are launched, they will have a random calorie value. However, for microcomputer systems, there is no concept of OS. We're talking about bare metal systems. There's no OS. So technically, those tasks, they're not process. They're different from the application process on a Linux system, on a modern system. They are tasks. They're just procedures. They're just the functions. And they have to share the same calorie as everything else on the system. Because of that, the same calorie value is reused everywhere. And sometimes those microcomputer systems, they do not even have the ability to generate high quality random numbers. So the calorie value is very predictable. So at runtime, the function is instrumented almost the same. There is a prologue, there is an epilogue. The prologue has to read that calorie value from somewhere, and the epilogue will compare that calorie value. Then if there is a mismatch, usually this underscore stack check failure function will be called. And we already saw that on Linux. When we call this function, we print out that stack smash detected, and also we kill this application. However, in embedded systems, not necessarily we can kill this system. We may enter an infinite loop, and sometimes that is not something it can easily manifest itself, right? When you kill a program and print out something, it's very easy to identify. But if the program is in an infinite loop, it's harder for you to identify it is in an infinite loop. So here is another program in the C library. So this is a version of the C library, and in this version, it clearly it shows where the stack calorie is created. It's actually here. You can see it here. So this is actually in the libc, the underscore libc start main function, which we have mentioned several times. So this function eventually will call the main function, right? Your function, of the C developer, your main function. This function will call that. And you can see that this function will set up the environment arguments, the command line arguments for your application, for the main function before it calls that. It will also do some initialization here and there. Also here, you can see this is architecture setup TLS, the thread local storage. It's going to set up the data structure for that. And there's other names for this data structure. So for example, there is a TCB. This TCB is not the security concept of trusted computing base. So this is thread computation buffer or whatever. Yeah. And you can see here, we have a global variable called stack underscore check underscore guard. And this local variable is the stack calorie value for the whole process. Okay. Only one value of that. So this global variable will be, this is actually a local variable. There is a global variable you set up using this macro thread set stack guard. Okay. And the value is from this local variable. And this local variable is from a random number. So we're getting a random number from that and put it there. Then we start your main function. So the paper stack guard was published in Unix Security 1998. And it was introduced as a set of patches to GCC because this is a compiler approach, right? GCC is not easy to develop and adding features to it. That's why in our research, we prefer to use LLVM, which is much easier to develop. And right now, a lot of production systems are also compiled with LLVM. Many of our Android systems are compiled with LLVM instead of GCC. Then several years later, IBM developed something called Pro Police. It places buffer after local pointers in the stack frame, and it helps avoid other types of corruption of pointers. I have a figure for that later. Then in 2012, Google engineers implemented this flag, -F stack -protector -strong flag to this flag will protect will add stack canaries to more vulnerable functions instead of all functions. So because overhead, you can see that the overhead of this is several instructions. If you want to add the stack canary to all the functions, it will be a little bit heavy, but some functions may not be that dangerous or vulnerable as other functions. Then using this flag, compiler will decide which functions are more dangerous. Maybe they are using functions like gets, string copy. Then for those functions, we will add stack canary, and others we do not. So right now, both GCC and LLVM supports at least those three flags. One is flash stack protector, then stack protector or, which instrument this to all functions and also a strong. So now most packages in Ubuntu are compiled with the stack protector flag. Things like already 10 years ago, and Arch Linux use this flag. So that's how this is used in real-world production systems. So this is the stack frame for the IBM approach through police. Let's say we have an example function. We have a function foo. The function has 4 local variables: an integer a, a pointer b, a buffer c, and bytes, and a buffer d, 3 bytes. Then the program is like we assign A's address to B, we copy some string from the STB whatever to the local buffer C. You can say this could be a buffer overflow there, because in the default GCC configuration or VM configuration, we already know what the stack will look like, right? So from the higher address will be local variable A. Then after that, we will have local variable B, then we'll have C, and we have D, right? So the compiler will reserve space for those local variables based on when they appear, right? If they appear early, they will have a higher address. So by default, the compiler will do that. Then you can see the vulnerability here is if you can override D, then you may override C, B, A, and also save the EBP return address. Right? You can override everything. If you can override C, you can override everything that has a higher address than that, B, and A. So the properties will change the order, the location of them on the stack. So it will put the buffers at a higher address. So B and C will be here. Then we have Canary. So now if you can override B, you can override C, but you will not be able to override A and B. But in this case, even if we have Canary here, if you override B, you can still override A and B, local variables. Right? In the very first challenge, we were overwriting one of those variables, not overwriting the safety EBP or readmaps. So this is the IBM approach. Okay, so next we are going to learn how to bypass this stack canary. So it's not that secure, at least for some type of programs, it's easy to bypass. So how do we bypass this? One way is we find another bug that is information leakage vulnerability. And through that vulnerability, we will know what canary value it is for this application. And that canary value stays the same. Okay, so that's one way. Because the canary value is only generated when this application is created. If this application runs there forever, the canary value is not changed. Of course, this is something we can improve. We can think about how we can re-randomize the canary value. That could be a small research project. Another approach is we can brute force the canary value. But every time we brute force it, when it's run, the program will crash, right? So let's say on a 32-bit version, 32-bit machine, the last byte of the canary is 0. Then we still have 3 bytes of canary values. If we brute force that, that will be like 60 million times. But it's 60 million times only if the canary value stays the same. But if it's one program, you give it canary value, the run canary value, you crash. So it's not 16 million times, right? But even if it stays the same, 60 million times, if it takes 1 second to guess once, if you compute this, it will be like almost 194 days to guess the current value. So, yeah, go ahead.
I want to make sure that I'm understanding this. When the canary value is generated, is that during compilation or at the start of the run?
The start of that application.
Okay, so when I run Volfu, it decides what the canary will be.
No, when you run Volfu, the program, the application itself
Yes.
may have been running for a long time. It's not generated when that Volfu function is created, is executed. It's the process is created.
Okay, so if the canary exists on, let's say, Microsoft Word,
Yes,
then when I double click the icon for Microsoft Word,
yes,
the canary is generated then?
yes.
Okay,
It could be a little bit more complicated than that.
yes, but
Because Microsoft Word may use multiple processes. Yes.
Yeah.
Mhm.
but
In general.
or
yes.
a random program.
Exactly.
Yeah.
Yes. So another heuristic is the fork system call will make a copy of the existing program. We already talked about that, the existing process. And it will not regenerate the canary value. You have a program. When you launch that program, you use exe-save-e to launch that, right? The system call is exe-save-e, and that is when the canary is generated. And this program later is forked to another program. Another program will copy everything from this program, including the canary value. Okay. So the child process will not generate a new canary value. In this case, we do not really need to guess 3 bytes of canary value at the same time. So if we get 3 bytes at the same time, we need 16 million times, a little bit more than that. We can actually guess the canary value 1 byte at a time, right? There are 4 bytes, and the 1 byte, we already know it's 0. Then we guess the second byte, okay? So we try to override the second byte. If our overwritten is successful, we find the correct one, the program will not crash, right? But if we overwrite to a wrong one, the program will crash. So 1 out of 255 times, it will not crash, and we figure out what it is. Then we move to the third byte, try to guess that. right? They'll move to the fourth byte. 256. So in total, we only need to try 700 times, more than 700 times to guess the Canary value. So this is the program we're going to hack today. The program is called bypass Canary. This program will create a child process, many child processes for you to crack. This is actually similar to some of our, let's say, web servers. The web server usually run a main process. When there are new incoming TCP packets, it will create new child process, use fork. So the child process will have the same Canary value. But in this case, we're not taking input from the network, we're taking input from a local file. Okay. So now let's read this program so we understand how this program works when we think about how to hack this. So in the main function, there is a big while loop. Okay, so this is your while loop. In the while loop, the first is we fork. Okay. At the very beginning of the program, we fork. And if the PID is 0, it will be the child process. If it's a parent, it will have a different PID. So after we fork, the original process, the parent process, will execute this part. And the child process will execute this part. Okay. So the child process will first print out the child process ID. Okay. Then it will call Overflow. So the child process is the one actually we are hacking. Okay, we're hacking the child process. After that, it prints out IPD the full, then exit 0. So in the parent process, it will print out the parent PID, then wait for the child process. So this wait PID is waiting for all of its child process. But for this program, there will only be one child process at any particular time. Then we have a global variable, a global buffer, or global variable called the global read, how many bytes we read. This is a Overflow function. Overflow has a local buffer, 40 bytes, has a file pointer, and Overflow also has a big while loop. In this while loop, it opens a file. This is a particular file under temp, and it's called exploit. So you are supposed to put your exploit in this file. So the child process will read from this file. Okay? If it cannot find the file, it will go back to the while loop and keep reading from that file. If it finds that file, then it will read from it. It will first sleep a little bit, then reset the global buffer, then try to read from the buffer, from that file. Read 70 bytes from the buffer, okay? That buffer is this global buffer. The global buffer is big enough. We're not trying to overflow that. Then it will print out the child process, read how many bytes from the buffer, and guess the Canary value is blah, blah, what, okay? It print out the Canary value we're trying to guess. Then after that, this is the vulnerability here. It's going to use memory copy from the global buffer, which is big enough, to the local buffer. Okay. And the length will be whatever you give in the exploit. So here, that's why this could be a buffer overflow, right? So here we're reading 70 bytes. And this could be smaller than 70 bytes. So that is why we have a buffer overflow. Then after that, we close this file and also remove the exploit. Okay. So let's say if the exploit is not able to exploit anything, it doesn't trigger a buffer overflow, what will happen? Let's say we only input 20 bytes. What will happen? We will just copy that 20 bytes to the local buffer. Then we will close the file, remove that file, and that's it. Then we go back to the while loop. So the child process will keep looking for new exploits, right? If that exploit fail to trigger any problem, you will go back to that. If that exploit is not successful, they're giving you a shell. However, it crashed the program. What will happen? It may crash the program because you override this. You override the stack frame of Overflow, right? It will crash the child process. It may crash the child process. After it crashes the child process, the parent will be notified. Child process is crashed, so the parent will go back to here to create another child process for you to have. Right. So let's try to run this. Okay, to do this, it's better to have two terminals, I think. Yeah, because one of the terminal we are going to we're going to use two terminals. The first terminal we are going to run this program. Okay, so see now we are running this program on the left-hand terminal, and we are running the main function fork. So we have two processes. One is the child process at the PID 57, the parent process 57, and child process 58, right? Two processes. And what is the parent process doing right now? It's just waiting for the child process. What is the child process doing right now? It's trying to read from that local file, right? So in this case, we don't have that local file. So if we give it some input here, so let's do echo hello to that process, exploit. So we input 6 bytes, hello 5 bytes, new line another byte, 6 bytes into this file, exploit. Then the child process will read that 6 bytes. However, we didn't put enough bytes there. We didn't even guess the Canary, right? So the child process will print the IP to the full, then quit. Then the parent process will create a new child process. Okay. So if we put many more bytes here, what will happen? Yes, we will crash which one? We will crash the child process, then the parent process will create a new one for us, right? So when we do this non-string goes to here. The child process read that non-string, read 70 bytes, and the child process will think we are guessing the Canary value is 67, which is G in X. We guess the 4 of those, and it's not correct. Because it's not correct, we get a stack smashing detected. That is a libc function stack check failed, right? Then this program where the child process will be terminated and the parent will create a new child process. So the parent never changes. Parent is still has the PID 57, but the child process is a new process. So now we want to hack this program. So how do we hack it? The first step is to disassemble this program, find where the canary is, and this is what the buffer looks like. We can verify this. With the OBJ dump. We're looking for the function. We're looking for Volful. So this is Volful. We know the block is at memory copy. So this is memory copy. Where are we copying to? We're copying to EBP minus 34 in text. Okay, 34 in text, that's 58. No, 52 bytes. Okay, so that is where the buffer is. So where is the canary? Let's see where the canary is up there. So canary, it's here. GS14 is moving to EBP minus 6. Okay, so canary is still at EBP minus 6. So let's say we have saved EBP up here. Then we have canary value. Here's our canary. From here to here is because EBP always points to here. So from here to here, we actually have the same, which is 12 bytes, right? That's our stack. Then we also have we have the buffer. The buffer is at this whole thing is 34, which is 52 bytes. So to override the canary, actually we need to override this 40 bytes, this whole thing 40 bytes. Then we put the canary there. For the canary value, which one is 0? I remember last one too. There are 4 bytes. I remember last one too. We can actually take a look to say which one is 0. Which one can we here? We debug this program. Name wrong. Okay. So at this point, we do not have the canary value yet. No, we don't have the canary value on stack yet. So after here, after this one, we should have the stack, the canary on stack. We can set a breakpoint here. Set a breakpoint and this. Star. Okay, so right now we're at this instruction. We just finished setting the stack canary value at EBP minus 6. So EBP minus 6 right now should have the canary value, but because we debug the program, this is a random value. So if we don't debug, we run it, we're getting a little bit different value, right? But still, we can from there we can say what the value is. So we examine let's say we do that 4 bytes. And it's the address of EBP minus C, right? Should be X. Okay. So you can say, oh, actually the first byte is 0. The first byte is 0. So 2C is address 0. Second is PA, CC. Those are random values. So I can prove that's random values if we run this again. We run this from beginning. Now we are at, I think we have 2 breakpoints. So we'll continue, and we examine this again. And you can say those 2 values are different, right? The very first byte is 0. Make it larger. The very first byte is 0 because it's always 0. But all other 3 bytes are different. EA, E6, 32, 7C, right? They're different. And in between, we rerun the program. So every time we run it, it will have a different value. Now we figure out. So how do we want to how do we want to hack this anyway? The stack is executable. Okay. How do we want to hack this? Yes, we still put share code. So we put a share code in environment variable. Let's say that. Then we write a script to guess the Canary value, right? We guess 1 byte each time. Eventually, we can guess all of them correctly, 4 bytes. Then we override. Then after we guess it right, we override this part, right? We override it with its original value. Okay. Then after that, we still override the saved EVP, then return address. That's how we are going to get a plan. And I have a semi-automated script to show you. You can make this fully automated, okay? But what I'm going to show you is semi-automated. This is Python 2 script, very simple. This script, we're going to put it in /10. This script will check. So it's also a big loop here. So the loop from range from 0 to 255. So it will first check if this exploit file already exists. If the exploit file already exists, it will just sleep 1 second, wait for the charm process of that program, the victim program, to retrieve this, read from this, and delete it. Okay. After it is deleted, if this one doesn't exist, it will create a new exploit file. Okay. With write permission, we're going to write this. Then we're going to write this. We're going to write 40 bytes of garbage. Okay, that's a 40 bytes of garbage. Then we're going to write since the first byte is 0, we're going to write 0, 0 there. Then we're going to try the second byte. Right. So in this case, yeah, we should write a 0, 0 there. Okay, make sense? Okay, so let's try this. The first step is put the share code there. Let's put the share code there. Very nice. Put the share code there. Let's see. Another zero. This is cat flag circle. Okay, looks like it's there. Okay, looks like it's there. So we have 1500 bytes of 1500 bytes of not stack. Now we do a flux. We create two terminals. Let's verify again whether it is still there. Answer to yes, so good, it's there. So both terminals and those terminals will still have that. Okay, so its address is the share code somewhere FF E8, and we can just simply use B line, I guess. Just B line FF. Okay, let's use that. That's our share code address. Hopefully that's 9, this is 8. Should be okay. So now we have share code there. We are going to create, we use our template, code template. We use the right-hand terminal for the exploit. So we go to then we next we create. Now we're creating a Python code, right? So let's just call it ePython. Oh yeah, this is a Python code. We're not going to. It's just created a code first. Then we need to change mode of this to make it executable. So plus X means make it executable. Now we are going to edit that. Max. You can use any tool you're familiar with. Copy this. Oops. What's wrong? So this one should be here. One should be here, right? This one should be here. F open should be here. Fine. Code. Main. What? It's from 0 to 255. Okay. Okay, maybe, but let me fix our problem here. So those two should be at the same level of the file, right? Those three. Yeah, those should be the same level of the file. This one should be here, this one should be here, this one. Okay, you said this should be 156 because it's not inclusive there. Okay, something like that. Here looks good. Here looks good. Okay. Then here we need another byte. Right. And this one looks fine here. Looks correct, right?
There shouldn't be a space.
Where?
After the back. First. The first line, very first line. There's a
Very
space.
first line. Oh, here?
Yeah.
Literally no space? I guess it doesn't matter. Anyway.
We need to add a blue before the null byte.
Hmm?
We need to add a blue before the null byte. Yeah, the null byte. Because
This B?
that's one. Before the null byte. So we try to get rid of it.
Here? Okay. Let's try to run this first. Let's see what we get.
Right.
Oh yeah, you're trying to file, so we should be able to see the file here, right? Let's say export file. Is that what we want? We got 40, we got 0, got 2 0. Oh, looks correct, right? We got 2 zeros. That's what we want. The first 0 is hard coded. The second 0 is because it's the very first increment in the loop. Okay. So, this program will also, okay. So we just run this program there. This program will monitor if there is an exploit file, right? Okay. So this program runs. Then we go to the left-hand side terminal, and we run this program. Okay, so now we are guessing. Okay. So let me know when you do not see the stack smashing, then we go back to here to stop this program. So see, the last byte we are guessing 0, okay, hard coded. But from here, we're checking one by one, and we're brute forcing this one, right? So if it is correct, then we should not be able to say the stack smashing detected string there.
I'm deeply embarrassed to be asking this. What command are you using to save and exit Emacs?
Control C, no, Control X, Control S, that's save. Then if you want to get out of that, you do Control C, you do Control X, Control C, yeah.
Thank you.
So someone keeps an eye on that. Let me write the. You can use VI or whatever. Okay, so you want to say it's Control X, Control S. You want to exit, it will be Control X, Control C. Forget. Oh yeah, the big number. But this part is correct. That's why we're showing that, right? Oh, here, I repeated the four. See that? Okay, I stopped the right hand side. Where is it? Here. I repeated the four, right? That's what we're looking for, which means after 0, 0, the value should be 79. So we go back here to think this. Exploit. That's why I'm saying this is semi-automatic. In the homework, there will be bonus points if you make this fully automated. But you basically read the output of this, right? So we have that, then we have 79, right? Or 76. 79. So this part, we didn't stop it, okay? The parent process is still running. So now we run this again. When we run this exploit again, the left hand side should keep showing things, right? Okay, that's correct. So now we are guessing the third byte. Right? So imagine this is a web server taking input from network. And this is how you guess it. We're just simulate that in a local file. Or at AD, did we miss it? Because no one is paying attention. Or it's really a big number. Maybe we missed it. Maybe we missed it at the very beginning. Hmm. Right. Yeah, we missed it. Let's try again.
So would a sign then that we get it be that the file hasn't been deleted after a run? Or,
The child process for deleting that.
okay.
The
Go
child
figure.
process is responsible for deleting that. Oh, yeah, see, it's a small number. No one paid attention. See?
Watching mine.
Yeah, no one paid attention. It's just one B at the very beginning. Yeah, we all missed that. Okay. Okay, so now we're going to guess the last byte. 1B here. 1B, 1B, yeah. Okay, now we are guessing the last byte. Okay, got it. What's the value? 96. Okay. So 96. Now we don't need this part. What is common in Python? What is common? I want to delete this one. Yeah, we don't need this one. All right, delete this one. That's why. Okay, so that's our Canary, right? After that, how many bytes we need? We need 8 bytes. Garbage? No, 12 bytes. So we have this 4 bytes. We need this 8 bytes. No, 12 bytes. This is 12 bytes. Then we have. So we need another 8 bytes of garbage. Okay. Then another 4 bytes of the address. The shellcode address. So this will be FF. I'm gonna put DASS there. Okay. We're done, man. So this is good. 40 bytes. Query, 8 bytes, shellcode address. I think that's correct. Okay, let's try. Okay, so now when we run this, we're supposed to get the flag here. And there's a loop, so I keep sending, so technically well, no flag. Right? Up down. Which part is wrong? So we have where the apple from? So we have oh, we have the line there. Okay. The line. So A should be fine. Yeah, A should be fine. So the color is correct. Um, that's why we do not get the smash stack thing. The we are overwriting beyond that. What? Oh, this is 12 lines. It should be 12, okay, not 8. Yeah. So these types there. Yeah. Nice catch there. Okay. For now. Yeah, that's how we get the back. Right? But keep sending it, but always get it back. Are you asking why we're not getting a segmentation? Yes, because when you get when in a chart, you get a segmentation fault. That chart process will be terminated. Then the parent process will create a child again. Yes. Yes, yes. Because you copy from the parent, so the canary is not changed. Yes, the parent, we, in this program, we never directly attack the parent, we're attacking the child. Yeah. Cool.
So if we have a new process, the canary will be changed.
What do we mean by new one?
Like we just terminate the parent process.
Yes,
And then we create a new one. And
yes, that will be changed.
So we have to like do all of those things.
Yes,
out.
that's why the left-hand side, I didn't touch anything.
Uh-huh.
It's always running the same parent process. Whenever I was always doing things on the right-hand side.
Oh,
Yes, never did this side. Yeah. Okay. And we still have, let's see, we still have like 20 minutes. Okay, so in the next 20 minutes, you can work on the homework. So this one will be the homework of the next week. So you can work on it now, or you can wait a little bit. You can work on behemoths. How many of you got this? Behemoths 1? Okay, so we already got that. So have you finished those two as well? Reverse engineering ones as well? Okay. Cool, then you guys can working on that. I will be walking around to help you.
Yeah, yeah, that's, when you need a lot of layers. Yeah. Let's say, for this family, we got to, we should talk to this family, we got to. Yeah, when you're talking this family, yeah, you're talking with instruction. Next family, you're figuring out the ambulance. That's why. This ambulance is fucking this that. Yeah. You get it.
Look at my credit card for the unit. I really struggle with that. And I just had it above the red
Like, so here.
right here. So I've got 71 bytes of garbage data. I've got the new return address, which should code point just above it. So then above that, I have a offset
Okay.
and
I would suggest make the offset much bigger. And also. Figure out what you have to do. Solving values. Where did you get the address?
I got it from DVD. I just through the address. Yeah, right here.
Oh, you don't even know to do that. You have an address. Add a menu.
Oh, I did. I added.
You said this is that.
I adjusted it myself in notes, but let me get it again to make sure. And I can also make sure that I'm doing it right. But I did.
Because in this page, you are also putting that in the environment variable. I think not, yeah.
I'm not putting anything in the indentation.
No, you're putting it in the.
I'm putting it in
formula
the
item, right? You're putting it in command items. And those command items eventually go to the environment variable. Oh, no.
No,
No, we're trying to find.
I'm not.
Yeah, yeah.
Okay, so I'm gonna break its name, run, and then I think I just did. I examined DP.
No. Wait.
So I don't know why this is completely wonderful, but so you create a, so that's why I pushed up to 488.
Yeah. It's probably even.
Okay, so I'm gonna go to, okay. I'm not sure what's been happening. For password. The authentication failure card.
So which share from you?
Where I grabbed it, I thought it was secret, self government, but they, like, the clients. Now this.
From downward.
The phone doesn't work.
This one is the hand flag, so this one downward. Now with the share. Yeah.
Also, not totally sure where I'm going to find the password once I'm paying. I've been working with the getting the self code or getting the check.
But it's fine. Alright.
Okay, so. Well, let's go through it.
One. Oh, you have another one. Nice one. Oh, how are you done?
I think I do need that
Yeah.
one. Yeah, I don't think I need the list.
Okay, yeah.
And then opening it. This part is the full Python code, right? Because this is the print statement, but
Right.
have to get a right there. By the Python.
There.
I'm pretty sure that we talked about it on Tuesday. My methodology of just putting it at five, that
You should work, but make the job a little bit harder. Um. Cool. Wow. Next, just a little higher end. Because the offset is huge.
58.
Yeah. About what? About higher. The white.
You sure it's 71, maybe I have that my mouth.
Forty-three, right?
44. Oh, yes.
43 is. 40 is 64. And 64. Plus 3, 57. Plus 4, 71.
Yep.
71 is good. 33 dollars.
Didn't know then you don't.
Why? Wrong with them? Yep. What's wrong with them?
No, and then after printing the screen,
Okay, see you guys.